This video is about transformations, and specifically we'll look at a vertical stretch or shrink. And so for our definition, before we dive into it, let's recall something very important, which is that when we refer to y equals f of x, we're referring to the parent functions, and there are 5 of them we're working with right now, as seen in the introduction video to this topic. So anytime we see f of x, we'll refer to one of our parents and then see it in the examples that follow. For our definition of a vertical stretch or shrink, we'll say it this way: to graph y equals c times f of x. Okay, so notice the c value. C is some number, as we'll see in a second. If the c value is being multiplied in front of the function f of x. It's like c times f of x. Okay, well, if c is greater than 1, we're going to stretch the graph of y equals f of x vertically. So this is the stretch case, by a factor of c. Now, what does that mean, by a factor of c? We'll see that in a second, but for now we're just understanding the distinction with the value of c. On the other hand, if c is somewhere between 0 and 1, not equal to either, but somewhere between 0 and 1, then a shrink will occur on the graph vertically, again by a factor of c. So let's take a look at not only some provided diagrams, but then also some more detail on how this actually happens. A vertical stretch or shrink actually happens in the following way. So when we're actually conducting the stretching or shrinking, the fair question is, what do we do? How do we do it? So we're going to multiply the y-coordinate of any point on the parent function by c, but keep the x-coordinate. So every point on the parent function, of course, has an x and a y-coordinate. We're going to address the y-coordinate. We're going to just leave the x alone. Now note, if c is greater than 1, you can see in the definition above, that is the case of stretching. When we multiply the y-coordinate by c, it makes it larger. Or you could say more negative if already negative. This gives the appearance of stretching vertically, or in other words, this is more also visual, stretching out away from the x-axis. Of course, if c is somewhere between 0 and 1, as we saw in our definition above, then we do the same thing. We're still multiplying the y-coordinate by c, but this time it makes it smaller, right? A value between 0 and 1 could be like 1/2, 1/3, 1/8, anything between 0 and 1. When you multiply a number by those types of fractions, the result gets smaller. Or you could say less negative if it's already negative. This gives the appearance of shrinking vertically, which means shrinking inward toward the x-axis. Let's look at an example where we want to do the following items. We want first to identify the parent function, then we're going to graph the parent function using a dashed curve, then we'll describe any transformations that occur in our given function, and lastly, graph the new function using a solid curve. Our first example is the function f of x equals 1/2 times the absolute value of x. If we recall the parent function options we have, then f of x equals the absolute value of x would be the parent function that matches the structure of this given function the best. And so let's go ahead and, secondly, part B, graph the parent function, absolute value of x. You'll recall that that has a point at the origin, and then in slopes of 1 or -1, points kind of climb up and away, forming a sharp V-shaped graph away from that vertex origin point. So there's the graph of our parent function with dashed line segments or curves. Then thirdly, we're going to describe the transformation. Now, notice that in front of the absolute value for this given function, we find a 1/2, and specifically the 1/2 is being multiplied in front of the absolute value. So what that tells us in the language of our definition is that c equals 1/2. Now that matters because we have to decide whether this is going to be a shrink or a stretch based on that c value. If c is 1/2, you'll look to the definition and find it's the case where c is between 0 and 1, which means this is going to end up looking like a shrink. That's the case we have here. And how do we do that actual shrinking of the graph? Well, as we saw in our note above, we're going to multiply the y-coordinates of each point by 1/2. Now, we can do that visually. These are nice integer y-value coordinates in this parent function. If the numbers get nasty, it can get nasty to multiply by 1/2, but it's not too bad here. Just to be clear, I'm going to use a different color to represent these transformed points. If I multiply all the y values of all these parent function points by 1/2, notice the origin point, the vertex, the y value is 0. If you multiply that by 1/2, you still get 0, so that point doesn't move anywhere. But let's take the point, for example, 1, 1. That will bring that y-coordinate of that point down to 1/2, which will just slide the point down. Its new coordinates would be 1, 1/2. So it's half as high as it was. If we do this with the second point, let's say the point 2, 2 originally on our parent function, if I cut that y value, which was 2, in half, it'll become 1, so that point will actually shift down to be the new point 2, 1. If we follow this with several other points, we'll see that they keep getting cut in half, and we end up with a line segment which is much more shallow or low aiming than the original parent function branch of this absolute value graph. We'll do that, of course, the same on the opposite side, on the left side where x values are negative, and find the same type of behavior. And so with these new transformed points, each being transformed by a vertical shrink in this case, we'll go ahead and connect the new points with a solid graph to form the new transformed graph, which is by appearance a wider opening absolute value V-shape graph. Our next example has the function f of x equals 2 times the square root of x. We'll go through our same process or steps on this one. First, identifying the parent function. In this case, the parent function would be f of x equals square root of x. We'll go ahead and graph the parent function with our key points 0, 0, 1, 1, 4, 2, and we'll use a dashed curve to represent the parent function. For part C, we'll identify what transformations are occurring in this new function. You'll recall there's a factor of 2 in front of the square root of x in this one. This is 2 square root of x. Well, that 2 means that our c value is 2, if you're looking back at the definition. Of course, with a c value being greater than 1, we are expecting to see a vertical stretch in this case. Let's recall how we conduct that stretch and then actually do it. It's going to involve multiplying all the y-coordinates of our parent function points by the c value, in this case 2. So if I multiply 0, 0 y-coordinate by 2, I still get 0, which means the origin remains one of our points. If I take the point 1, 1 and multiply its y-coordinate of 1 by 2, I get the point 1, 2. If I take the point 4, 2 and then multiply its y-coordinate of 2 by 2, I'll get 4, 4. Okay, and this could continue on. But now with these 3 points in play, we can see, I think clearly enough, that the shape does get stretched vertically. It's just going to be curving up a lot higher than the original square root of x parent function.